Yes, the floor is yours now. Thanks.
Okay. Okay. Hi, I'm a principal software engineer in Arm's IoT line of business. I'm here to talk about a project I did earlier this year. So the project all started around my coworker David Henry's office. So he built an office in his backyard to work in home in when he's not in the office. So as you can see, it's a nice isolated place to work in home in. But it's separated from his main house, so he wasn't being notified when someone was ringing the doorbell to deliver a package. So given we both work for Arm and in the IoT business unit, we decided to solve it using machine learning and a microcontroller. So the goal is to have a microcontroller in his main house that's continually listening for audio data, and it has a machine learning model that can detect a doorbell sound. And then when this happens, it's going to use the Wi-Fi connectivity portion of the microcontroller to send a message to his phone using the cloud service. And one of the benefits of this solution is since the ML inferencing is done on the device, it's going to preserve the privacy of his house. So no audio data is going to leave his house, which is really good for us and him. So every machine learning solution should begin with a data set. So rather than collecting my own data, I found there was this FSD 50K data set, which contained 144 doorbell sounds. So I decided to use that as the training set for the model. And with audio classification, you need other sounds to balance out what you're trying to detect. So the FSD 50K data set also had classes for music, domestic home sounds, human voice, and hands clapping. So these are the 5 categories that the audio classification model is going to use project. And I've seen this audio classification before. When I was a software engineer at Arduino, we launched this popular board called the Arduino Nano 33 BLE Sense, and the TensorFlow Lite team had ported the popular keyword spotting example to this board. So this one detects yes, no, silence, and unknown sounds. So I decided to see if the same model used in that example could be reused for this board, for this project. And then if you open up the example, you'll see a C array containing the model, which is hard to read, but if you convert that to a binary file and open it in this app called Netron, you can see the model structure. So you can see it takes a 49 by 40 input and then passes it into a depth-wise 2D convolutional layer. And then the output of that goes to a fully connected layer with a softmax output for the 4 classes I mentioned before. So the goal is to try to reuse this model structure in the project rather than inventing our own model architecture. So way back in 2019, when the TensorFlow Lite team was developing this example, there was only TensorFlow Lite 1. It's a bit hard to see, but you can see there's many lines of code on the left-hand side compared to the right. So with TensorFlow version 2, it's much easier to build this model. You can do it with less than 10 API calls. So that was something really nice about working with TensorFlow 2. It's more concise to make the same model to solve the same issues. And it's a bit tiny to see, but you want to use the same parameters. So for the kernel size, it's going to be 10 and 8. And the strides is going to be 2 by 2, just like that model. And it's going to use a ReLU activation, same padding, and a depth multiplier of 8. And then you can have a flattened layer to pass on to the dense layer. And instead of 5 output classes, we're going to have, instead of 4, we're going to have 5 output classes there. Okay. And the next step is how to get that 49 by 40 input to the model. So here you can see I recorded a doorbell sound at my house, and this is what 1 second of audio looks like for a doorbell sound in the time domain, and it's using a sample rate of 16 kilohertz. So if you look at the TensorFlow README for the example, there's a section on preprocessing. So this gives us some hints as to what what you need to do. So they're showing here 30 millisecond frame length. So at a sample rate of 16 kilohertz, that's going to be 480 samples. And similarly for the frame step that they're moving the window by, that's 20 milliseconds. So that's going to be 320 samples, and they selected an FFT size of 256. So again, TensorFlow has a very nice signal processing package. So we can create this audio spectrogram using 2 API calls, passing in the 48 frame length and the 320 step size that we determined before, and the FFT length of 256. So this gives you an output of 49 by 129, which is not the 49 by 40 that we wanted. But on the diagram, you can see around 4,000 hertz. That's when I initially pressed the doorbell. So you can see some sound on the spectrogram there. And then there's some ringing under 1,000 hertz. And then when I release the doorbell at 3,000 hertz, there's a line there. So to get down that 129 to 40, there's something called a Mel Weight Matrix, which maps how humans perceive audio signals to regular frequencies. So on the graph there, you can see in lower Mel bins, there's a one-to-one mapping between the FFT bin and the Mel bin. And then higher frequencies, or higher Mel bins, it covers a broader range of audio frequencies. So if you use that matrix, we can convert our spectrogram to the correct dimensions that the model expects. So here I use the tf.io Mel scale function to pass in the spectrogram, and it converted it. You can see there's less white space at the start because of the Mel frequency adaptation. And then one more step would be to convert that Mel spectrogram to a power spectrogram by applying 10 log Mel squared divided by log 10 to that. And you can see now it's logarithmic scale. Okay, so just to recap, we can convert our 16,000 samples of audio for 1 second audio to the Mel power spectrogram, and that's the right shape to feed into the model that we developed using TensorFlow with Keras v2. And the ML classifier is going to have 5 classes, so the doorbell, the music, domestic home sounds, human voice, and fingers clapping or snapping. So the next step is to actually train the model. So TensorFlow provides a tf.data.dataset pipeline, which can be used to pre-process your training data in parallel, so it can do things really fast instead of sequentially. So the first step in the pipeline is going to be reading the binary data from the file using tf.io.read file. Then we'll decode the wave file using tf.audio.decodewave, and then resample any samples which aren't 16 kilohertz to 16 kilohertz using the resample function. One extra step I did is to trim the silence from the beginning and the end of the audio samples, just so that's not in the training data. And then the tf.signal.frame API can be used to split up the longer audio samples into 1 second chunks, which we need for processing. And we'll stride over the lengths at 0.1 seconds. So from one wave file, you'll have many samples to train the model with. And then once you have all those 1 second clips, you can pass it to the Mel power spectrogram functions that we covered before. And then for training the model, I decided to split it up into 2 phases. So there's another data set called ESK50K, which has 50 audio classes. And I found that data set is more robust than what's in the FSD50K data set. So first I trained a model on that data set, and then I reused the weights from the depthwise convolutional 2D layer in that model with a new model with an output with just 5 classes. And then once that model is trained, I converted it to a TF Lite format with inputs and outputs and quantized weights. Okay, And then the next problem is how do we send a message to a phone? So there's a company called Twilio, which offers a REST service to send SMS messages. So you just need to do an HTTP post to the URL up there with the credentials shown in your developer console when you log into Twilio. The username is going to be your account SID. The password is going to be the auth token on the web page. And the request body is going to have a to section, which is the phone number you want to send the messages to. The from is your Twilio number that they give you with the service, and the body is the message of the text message. Okay, and now for the hardware platform, I decided to use a SparkFun AzureWave ThingPlus board, which is based on a Realtek SoC. So this provides a Arm Cortex-M33 compatible CPU called the M300, and that runs at 200 megahertz. The board has ample RAM to run the model, so it has 512 kilobytes of SRAM and then 4 megabytes of PSRAM, which I'm not going to use in the project. I'm just using the SRAM for now. And there's lots of flash, so there's 4 megabytes of flash, and it has built-in 2.5 and 5 gigahertz Wi-Fi connectivity to connect to the cloud. And then on top of that, it also provides a hardware audio codec, so you could plug in an analog microphone and start getting audio data from that. And the Realtek team has also provided an Arduino core for this, so you can program the board using the Arduino IDE. And unlike the Nano 33 BLE Sense, there's no microphone built in, so you need to use an external one, but you can just connect it to 3 wires, the 2 powers for power and ground, and then the audio signal on pin 22. Okay, another good thing about the Arduino ecosystem is there's lots of libraries to build your application on top of. So the first one I'm using is called Audio Codec, and it's built by Realtek. So this will give us a way to control the audio codec. It's going to provide us with audio data at 1024 bytes at a time. So if we're using 16-bit samples, which are 2 bytes, it'll give us in the audio data in chunks of 512. So if we divide 512 by 16,000, we'll have 32 milliseconds to process the data in real time. Another library that Realtek provides is the Wi-Fi library that allows us to connect to the Wi-Fi network and provide the UDP and TCP sockets you need. And then the Realtek team has also ported the TensorFlow Lite library to run on the board, and this includes Arm CMSIS-NN library, which will give us accelerated computational kernels for Arm Cortex-M processor, which is running on the board. And then finally, for the DSP steps to create the spectrogram, I used the Arm CMSIS-DSP library, which is also included in the Realtek package. And the last library I'm using is the Arduino HTTP client made from Arduino. So that will allow us to call the REST API from Twilio. Okay, so Arduino sketches usually have a setup function that's run once when the program starts. So this is going to, in this example, it's going to initialize the DSP pipeline, initialize the ML model, connect to the Wi-Fi network, and start the audio codec library for microphone input. And then our loop function, which Arduino runs continuously after the setup is called, is going to wait for new audio samples, update the Mel spectrogram with the new audio samples that it got in, perform the ML inferencing using TensorFlow Lite, and then one additional step I've done is called exponential smoothing. So rather than directly using the model output, we're going to sum it over time with an alpha factor. So it kind of smooths out the output because the audio data is noisy. So we don't want to make decisions based on noisy output from the ML model. And if we do detect a doorbell sound, and it's been 30 seconds since the last time, we can use the Twilio API to send the SMS message. So all the code for this is on GitHub. I'll show the link in the next slide. But in terms of processing time, the Mel power spectrum calculation takes 3.4 milliseconds on the board. The model inferencing takes 14 milliseconds. So that gives us 17.4 milliseconds for the model and the DSP to run, which is well underneath the 32 milliseconds that we needed to do it in real time. So if you're looking to do more advanced models, this can be quite a good platform because you have ample compute to do so. Okay. And then, so a recap is we use the SparkFun AzureWave ThingPlus board. We combine its audio, compute, and connectivity capabilities together to listen to doorbell sounds in David's house. And then once that was detected, we used the Twilio cloud service to send a message to his phone. If you want to learn more about this, there's a demo at the ARM booth just over there. And there's a few other demos as well for you to check out. And I'll leave the links up here for you to read more on the blog I did and the project on GitHub. Okay, that was it.